As we discussed in previous units, forensic investigators examine physical memory content to detect malicious processes, threats, and memory-resident malware to recover passwords and encryption keys. In some cases, forensic examiners will not be able to start a forensic investigation without having the physical memory content. To start memory acquisition, let's learn some well-known Windows memory acquisition tools. The open-source Monsource Windows Memory Toolkit is a host-based Windows memory acquisition toolkit. It is very easy to use. When you run dumpit, a tool from this toolkit from a USB, the raw memory dump will be generated and written to the same directory you are running dumpit from. The other host-based Windows memory acquisition tools I recommend include winin.exe from Guidance Software, MemoryDD from Mentech, FTK Imager from Access Data, and the Belkasoft Live RAM Capture. The commercial tools such as FResponse and the Forensic Toolkit allow examiners to conduct forensic acquisition remotely by running an agent on a suspect machine. Once we have a physical memory image dumped, how do we extract information such as running processes, registry data, event logs, network traffic, and web history, etc. from the memory image for forensic analysis? We use a command called strings to extract printable strings from Linux memory dumps. But strings does not give us all of the variable information we need. Let's study some memory analysis tools that are capable of extracting processes, network, registry information, even password from a memory dump. Some of these tools also work for Linux Unix memory contents. Windows Scope is a commercial tool for Windows memory acquisition and analysis. You can get a 1 month full-featured trial to try out this tool. One of its strengths is the detection and the reverse engineering of rootkits and malware. Redline Memorize from FireEye is a free tool for Windows memory acquisition and analysis. The open-source Python-based toolkit called VarAuthority Framework is able to extract information from both Windows and Linux Unix memory images. Let's closely look at VarAuthority Framework to understand how memory analysis tools extract processes and other information. VarAuthority Framework requires an acquired memory image as an input. To start a memory analysis using VarAuthority, you should run the VarAuthority plugin image info first to identify the operating system service pack, hardware architecture, and the address of kernel debug structure from the given memory. So here, the given memory is called mem file. The image info output tells you the suggested profile of the image. For example, WinXP SP386. You will pass on this parameter when you run other plugins. Knowing this profile information, VarAuthority will use the kernel debug structure to point to kernel objects and structures, which contains processes and network information. For example, a Windows kernel uses eProcess data structure to store information for each running process. All active eProcess are double-linked together. This linked list of eProcess structure is pointed by PS active process head. VarAuthority uses kernel debug structure to find the PS active process head and then to list all current running processes by traversing through the eProcess linked list. VarAuthority Framework supports a variety of plugins, including PSList, PSScan, DLList, modules, and connections, ConnScan, HiveList, etc., to allow us to extract processes, threads, registry, network connections, and many crucial information. PSList plugin instructs VolAuthority to use PS Active Process Head to list all running processes. To run VolAuthority framework with plugins, we will provide the profile we learned from the plugin image info. So here's one example using a plugin PSList. However, to hide processes, rootkits simply unlink these processes from the eProcess list. Once unlinked, although these processes continue to run normally, they will be hidden from most standard process enumeration tools such as Windows Task Manager and sysinternals utilities. The VolAuthority plugin PSScan does not use the linked list of eProcess. It scans memory looking for eProcess structure that represent processes and returns the physical address spaces for all eProcess objects. Therefore, PSScan will list all processes, even the processes are hidden by rootkits and are not shown by PSList plugin. Any discrepancy between outputs shown by PSList and PSScan may indicate that rootkit is likely installed on the suspect machine. Similarly, the plugin ConnScan can extract hidden network connections, while the plugin connections cannot survive from the malicious attack. The plugin CryptoScan attempts to recover encryption passphrase from a memory image. Here is an example of using CryptoScan. For Windows memory images, VolAuthority framework uses plugins HiveList and HiveScan to dump out the registry hives such as SAM, security, software, NTUser.dat, userclass.dat found in memory. Google's open source Recall memory forensics framework, in terms of functionality, is very similar to VolAuthority framework. In addition, Recall is able to acquire Windows, Linux, and Mac memory images. VolAuthority framework does not have the acquisition function. In the demo, I will show you how to use VolAuthority framework to analyze a memory dump